Right? Those things to consider. Okay, so what position is the chemistry at? So if you can identify where chemistry is happening, right, both in the reactant and the product, you can potentially come up with plans for how to run that reaction. Right? And in particular, acknowledging what kinds of chemistry would get you to that place or take you from that place. That types of chemistry is our reaction types: acid, base, substitution, elimination, addition, radicals. Okay? So if you know those patterns, you can try and place those reagents. If you don't know those patterns, you're shooting in the dark, okay? Which is one of the reasons why synthesis becomes so challenging, is you don't have the patterns on which to base it. Okay? Look for reagents or elements that are missing. That can help set you up with what reagents you need to use. Okay? This is ultimately just a guess at it, okay? Because then what you need to do is test it. Did that reagent selection work? Does it run the way you expect it to? If it does, then great, you've got a proper step. If it doesn't, then you need a different reagent stack. Okay? That's that advanced aspect. Consider the complications of the reagents you've chosen. Okay? Regiochemistry, stereochemistry, all of those aspects. Okay? So we saw this example. Should we walk through it again? Sounded like a nope. So we can take a look at some multi-step reactions. These ones are a little bit more challenging, but you do have the ability to complete all of these. Okay? These aren't officially synthesis. These are just running reactions. Okay? So let's see what you guys can come up with. Do it as much as you can for any one of them. Okay? And I'll give you a couple minutes to work on it. If you've got a question, raise your hand. So we could try and do resonance. That would be okay. So you're saying you're taking the pi, you're moving it up there. Negative, positive, OH.
I was also trying to figure out how BR and BR2 and BR3.
Okay. So BR2, you should remember how that reacts. How does that react? So we could see it as a radical reaction. Okay. Do we have any hints that we're running a radical reaction?
No.
There's no heat specified. There's no light specified. So radical is not the case. We hear backside attack. Backside attack means a nucleophile. Where's your nucleophile?
On the structure.
If it's attached to the structure, it is not a nucleophile. A nucleophile must have electrons. Once it leaves, yes, we have a nucleophile, but it must leave. For bromide to leave, what is it going to leave behind?
Bromine.
Try again.
Bromine.
If those electrons go over there, yes, we would get Br minus. Fantastic. What else would we get?
BR plus.
Br plus. Is Br plus stable? No. What is Br2? An electrophile. It runs completely counter to all logic that you would expect because of bromide. Bromide is not present. Bromine is an electrophile. Okay? That's why we saw it in addition reactions. Which type of addition reactions? Electrophilic addition reactions, because you're adding an electrophile. Bromine is an electrophile. Okay? Which would mean, what would we need to find? We would need a source of electrons, a nucleophile. We conveniently did that resonance with that negative charge. We could say, oh, well, the negative attacks. You'd end up with an OBr bond. Is that setting off any alarm bells? You're like, totally cool, that's fine.
No.
Okay. That's taking two very electronegative elements and putting them close to each other. Okay. That's a questionable call. Add on top of which, I like the idea of going through and doing resonance. What makes that first structure reactive? Polar pi bond. This is not a bad argument. It's a wrong one, The hydrogen. Really? Why would the hydrogen be reactive?
It's an acid.
Because it's a carboxylic acid. That's the name of the functional group, which means how is that likely to react?
Like an acid.
Like an acid, which is going to give you H+. What did we say bromine acted as? An electrophile, Br+. What does that mean? Shaking your head no is actually a pretty good response. Those two things are not reacting.
Does the Br2 have to react first?
Nope.
Yeah, so the PBr3 is going to pull off the OH,
Yes.
and then the bromine's going to go in.
PBr3 is a substitution reagent that replaces all OHs with
Br.
Br. So we're going to convert that not into an acid anymore, but now into a bromine, and then all these carbons. Okay? Awesome. Did that take advantage of the Br2?
Not yet.
Not yet. So what does that mean?
Keeps going.
Something's going to have to react to get us there. Okay? This is trickier because this chemistry relies on something very particular. What is that chemistry going to rely on?
Resonance.
Yes.
The pi bond moves, and then the Br could attack it.
Pi bond moves. Where's that pi bond going to move?
To the left. My left.
Okay? So you're going to suggest it moves down this way?
Yeah.
So we're taking electrons between a carbon and an oxygen, and those electrons are moving where? Milana, what's your issue?
I thought you would have to make the O would be polar, so negative, so bring it down and then kick off the leaving group.
Oxygen is more electronegative. So I like where you're going. You've got structural pieces, you don't have mechanistic pieces. Okay? That pi bond, if anything, is going to be going up that direction. That would make that carbon exceptionally positive, right? Right? Well, Br2 is positive. That's not going to stabilize it. So where could we possibly get electrons from to stabilize?
H2O.
H2O is not there yet. Br plus doesn't supply electrons.
Well, doesn't Br minus? If you have Br plus.
You don't have Br minus until you get rid of the Br plus.
Oh.
But don't you have zero or oxygen negative right now?
Then
Oxygen.
No, the oxygen's bound up in the phosphorus.
But I mean,
you have the hydrogen GH plus that we had earlier. don't you? Still.
It's getting better.
Well, or is it now part of that phosphorus group?
The bromine leaves and we have a positive charge. How do we stabilize that positive?
Add electrons.
We would need to add electrons in the form of what?
Pi bond.
Kinda, sorta. Where do you get a pi bond from?
So is it going to test the oxygen?
Okay,
You
so
have to eliminate 2 sigma bonds in order to get 1 pi bond.
there's some proper wording in there. If we took a look at, say, this reaction, we could go through and form a carbocation there, right? Very similar to what we've got forming up here. If we drew out a resonance structure, yada, 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 all those pi bonds, or all those carbons. We would need to stabilize that positive. We've got a bunch of atoms withdrawing electrons away, making that positive more positive. If we go here, how do we stabilize that positive?
Electrons.
We could give it electrons from where?
PBr3 has them.
Different reaction, right here. Below the line. Where do we get electrons to stabilize that positive?
All the other sigma bonds.
Water?
We could throw in water. What would water act as? A nucleophile, because it's sharing electrons with it. Except, we don't have a nucleophile. Where do we get electrons to stabilize that positive?
Sigma bond to Br.
A sigma bond to Bromine? So you mean bromide reforming the bond?
Yep.
Is that what you're suggesting?
Yes.
Yes. That does the reverse reaction. There's another option.
CH bond.
The what?
The carbon hydrogen sigma bond. There we go, yeah.
And what could happen?
You hold those down, yeah, like that, and then get H plus. Plus. There we go.
Why are we allowed to break that carbon-hydrogen bond?
Heat, light.
In the case of the elimination reaction, we have heat, okay, to weaken that bond. We typically also throw in a base if it was an E2. In this case, we know it's not an E2 because, again, below the black line. I don't care above. We would need anti-coplanar. I haven't really specified anything about anti or not, so yes, that's a true statement, but nothing about this would suggest one way or another.
You have a carbocation.
I have a carbocation. When do I form carbocations?
E1.
E1, in the one-type mechanism. Do I need a strong base in a one-type mechanism? No. Do I have a carbocation?
Yes.
Yeah. Do I need a strong base? No. But I would need to remove a hydrogen. Is there a hydrogen at that position? Would that hydrogen be acidic? Yeah, it should be even more acidic than the one down here. Why?
The oxygen.
Because it has an electronegative oxygen and an electronegative bromine all pulling electron density away from that center carbon, making that hydrogen even more willing to pop off so that we can stabilize that positive carbon. The hydrogen up there, above our black line, that red hydrogen, very acidic. What does that do for us if we remove that hydrogen?
Gives you the double bond.
Okay, so I heard a suggestion. It gives us a double bond. We could remove that hydrogen. We could form a pi bond.
It could.
That's an enolate. Where are enolates more stable? Typically, when we talk about enolates, they come with 2 extra terms out in front, or 1 extra word. Blank, enol, blank. Keto, enol, tautomer. We have an enolate here. What should be in front? Tyler?
You know, like keto?
Keto. What is a keto?
Ketone. That's right.
Ketone. Okay. Why is this important for us? What did we just discover? Say that again.
Nucleophile.
We now have a nucleophile. What are we looking for? A nucleophile so that
We could react with that.
it could react with the Br2. That should be exceptionally difficult for you. Why?
Because there's a boatload of electronegativity around the.
Why is that reaction difficult for you? You can also make the argument, no, that's not difficult for me. I totally understand that. I knew that from the beginning. I was just testing you, Mike. Except both.
A lot of steps.
A lot of steps.
We end up with something that is really weird looking.
It is weird looking. We went through this enolate form. We talked about that yet.
Yes or no?
Yeah, you're like, I don't really want to say no because you're going to be a jerk and say that yes, we have.
Well, I've seen it.
Sort of.
In our material, I've seen enolates.
The enolate has shown up in our material. It was officially in chapter 10 at the tail end. We hadn't gotten to it yet. Okay? This reaction is coming from the tail end of chapter 10. Okay? What are we doing beginning to end here? We started with a carboxylic acid and we ended with this weird structure. Overall, what reaction did I do? Look at it green, here to here. What does that look like?
Substitution and addition.
Substitution, right? And weirdly, two substitutions, right? I got rid of the OH and an H. I did two substitutions. Okay? The reason that could happen was because of this goofy enolate. Okay? Did we talk about enolates? Yes. Did we talk about how to react them? No. Okay? That's part of the context of that material. Okay? Are we done?
Not yet.
Not yet. Why do you say that?
We still have water.
We still have water. What does water have?
Electrons.
Electrons. What is that structure probably missing a whole hell of a lot of?
Electron.
Electrons. Where's the most electrophilic site in that structure?
Carbon.
So we have to be careful. Electrophilic, not electronegative. Okay, so electrophilic, which spot is wanting electrons?
C1 carbon.
That carbon wants electrons. The oxygen, being electronegative, is withdrawing electrons. Okay, through a pi bond resonance system, so very much making that carbon positive. That bromine, through induction, is making that carbon positive. This bromine, making that carbon positive, though albeit a slightly weaker, making it positive. So what does that mean happens? Water needs to attack that site. Do we have a weak bond that we could break?
Yes.
Yeah? Which bond?
The carbon bromine.
Carbon bromine. Why do you pick carbon bromine?
Because bromine is drawing those electrons closer to.
Less electronegative. And
Bromine is large. It can stabilize that negative charge very, very, very well. Okay? So what we'd end up doing as an argument is we'd either break the pi bond or the bromine. Our argument is that bromine would generate a more stable negative than if we broke the pi bond at this stage. Okay? In the third unit, we're going to talk about that in a little bit more detail because the chemistry that's happening at this point is actually third unit chemistry. Why on earth is it in chapter 10? Because Carty's not talking about that chemistry, he's talking about the substitution chemistry at the enolate position. Okay? So this is a tricky reaction because it's involving mechanistic stuff that we haven't seen yet. Okay? And won't see for a while. The end result, bunch of carbons, bromine, OH. Now beginning to end, what happened? Strictly a substitution. Hydrogen for bromine. How? Through all of those steps. Are you responsible for every single one of those steps? Yes.
It is possible to water attack the carbonyl carbons because of activating the two steps. Step 2.
Water is attacking here. That's when step 2 is coming in.
It's over here.
The water up here? Up here.
Yes.
No.
Because the carbonyl activated.
There's no water there.
Well, no. It's an empty first.
Okay. And that's what this, if we added water, yes, it absolutely attacks there and ejects that bromine and we get right back to the carboxylic acid. We never do the final substitution with that last bromine. Okay, the reason we go through PBr3 is so that we can get that carbon to become a nucleophile so that it can do that substitution.
So is that correct, that it attacks
The carbonyl carbon
carbonyl and then
ejects the bromine, yes.
like a step or?
You are fine with showing it that way. I think the default in most systems is to show it that way because you generate a more stable structure than if you break the pi bond. I would lean towards breaking the pi bond first, but mechanistically, we don't really have any evidence one way or the other. So we go with the shortest route with the best possible intermediates. Okay. Whoa, hello. What about the next one? What do we notice again? Br2, which means electrophile. Is H plus an electrophile? No. H plus is not an Sorry, you're right. H plus is an electrophile. Both electrophiles, which means what do I need to find here?
A nucleophile.
I need to find the nucleophile. Where's it going to end up appearing? We might go with the oxygen. The oxygen will actually act as a base to react with the acid.
So,
If it reacts as a base to react with that acid, what do we end up forming? Whoa, that was a weird flash.
some water.
You get an alcohol, and then you get an
Would I want a positive oxygen? I like what you're probably saying is do this. How do I stabilize that positive carbon?
Give the oxygen more to hydrogen and have it leave.
So a suggestion was give the oxygen another hydrogen so it can act as a leaving group. If it leaves, what happened to the carbon?
Stays positive.
Try again.
Oh,
Becomes negative.
It becomes more positive because the oxygen's going to take the electrons with it. So we do not want to protonate that oxygen a second time.
Proton transfer.
What did we do to stabilize that positive?
Hydride shift.
Right idea, wrong terminology. A hydride shift means doing this.
Oh, yeah, you're right.
That is a hydride shift. Did we make the carbocation more or less stable by doing a hydride shift? Less stable. So that was wrong idea. It's not a hydride shift you're talking about. What are you talking about? Deprotonation. Okay? If we just deprotonated, those electrons would go to the carbon, and just a deprotonation. So we can get better terms than that, because that would be a negative like that. We're not just doing a deprotonation. What are we doing?
Making a pi bond.
What is the process of making a pi bond?
Breaking
elimination.
An elimination reaction. So those electrons are better going to making the pi bond. So what could we do to stabilize the blue carbocation?
Take away some hydrogen.
Take away some hydrogens. The exact same thing we did in the previous system. Okay? Why is this one harder?
Where would you take it from?
What do you mean? Elaborate. Where would you take it from? I agree.
I'm asking a question.
Okay? Fair enough.
It's no longer.
Should you take it from this green hydrogen?
No,
Why not?
because it's not one pi bond. You have to have an alpha and a beta.
We need to be looking at the beta position, because when we think about eliminations, our term with elimination is beta elimination. You ever wondered why they called it beta elimination? The carbocation is located at position
Beta.
alpha. The beta position is where
The elimination.
you're removing the hydrogen to do the elimination. Beta elimination. If the carbocation is alpha, which hydrogen am I removing?
The beta alpha.
From the beta position. Why is this structure more tricky than the one up there?
Where's the beta position?
Which one is the most acidic hydrogen?
How many beta positions are available in the blue structure? 2. There's that orange hydrogen, there's the red hydrogen. If we go up to the previous example with our green one, how many beta hydrogens are there? There's just one. The blue one becomes trickier because we have 2 spots. How would we know which one to eliminate?
Alkenes substituted carbon.
Wow, that one's long.
More substituted
More
carbon versus less
substituted.
substituted
Pi
carbon.
bond.
So more substituted carbon, that's an awful lot of letters to fit in that first blank, so I disagree.
The innovator.
We've talked about a versus before. Where's versus shown up before?
16s.
16. Nice. We could try primary versus secondary. Not a bad idea. It's the wrong season.
Stable. Innovate.
Kinetic versus thermodynamic. One of these is going to be the kinetic enolate. One of them is going to be the thermodynamic enolate. What dictates kinetic or thermodynamic? Our reagent conditions. Okay? We're running under a very weakly basic environment. How weakly basic is it?
It's acidic.
It's acidic. So it is so insanely weak that we are going to favor which enolate? The thermodynamic.
Yeah.
So we're going to remove the orange hydrogen to make our pi bond. What happens after we remove that orange hydrogen? We would have what functional group? Enol. And which did we say was more stable?
Keto.
The keto. If we move to the keto, what do we find? We now find a nucleophile. So what can happen?
Your BR.
It can react with the bromine. We can put on the bromine. And we've done our substitution. What is pyridine? Except two answers. Sort of three answers. Invert stereochemistry is an awesome statement if we were talking about thionyl chloride. We're not talking about thionyl chloride. What did it do for thionyl chloride?
Made it open.
What does pyridine have? A leaving group?
Or like electrons.
Lone pair of electrons.
What could we do with the lone pair of electrons?
Make a bond.
Two. A hydrogen. Pyridine acts as a decent base. It's not the greatest nucleophile. Once we've done our bromine substitution, and we now throw in a weak base, what can happen? The pyridine can remove the hydrogen, making our pi bond. We'd end with our final structure. And look, we went full circle. What's that?
The BR leaves.
The BR ends up leaving. Whoops, because I didn't add that arrow.
What happened to the hydrogen on the pyridine grab that one too?
Pyridine only is grabbing this red hydrogen here.
What happened to the orange hydrogen?
What removed the orange hydrogen? The weakly basic environment. Okay. What is the specific base? Your guess is as good as mine. Okay. Look at your system, what's in there. At best, you've got lone pairs. Okay. So you might be relying on some unknown solvent that isn't specified in there. The details of removing that hydrogen aren't critical. We do need to know it is acidic because that would generate our keto-enol tautomer. And that keto-enol tautomer is exceptionally important.
You've got the H on, I see there. So in step 3, you take the electrons away from the H plus, but on step 4 you still wrote it as OH on the other one. I'm confused there.
Oh, I see.
That's what I was getting.
Yeah.
Where did that H disappear
Because what I actually meant to do was the lone pairs,
Oh, okay.
not the
So
hydrogen.
deprotonates because of, it's already.
That hydrogen is again going to come off the solution. This, as a tip-off, is actually coming right here. Does that show just H+?
It shows an absolute, which means excess.
An absolute, those are brackets. That's how they're trying to hint at it's a catalytic amount. It's just enough to help this reaction run. That's about it. And if you go through and look at your hydrogen transfers, they completely equal out.
So when it's excess, we say excess, though?
Yeah. Okay. Last one. What's different about this one?
We got a base instead of an
Hey, at least we got a strong negative right out of the gate. Would we expect that strong negative to attack bromine?
No.
Why not? What kind of bond would you form? Do you like that structure? No. So should the OH attack the bromine? No. Okay, so try something else. What should the OH attack? So we could go through and attack the carbonyl carbon, okay, busting that open, okay. We haven't learned that chemistry. That is now a nucleophilic addition. You're reacting with a polar pi bond. Nothing we've really done is talked about that. We will talk about that at the end of this unit. It's acetal chemistry, and guess what the acetal chemistry does? It reverts right back to the carbonyl. Okay, so while that is a valid option, it ends up being highly reversible, and it doesn't go anywhere productive. Where else could we find a positive? Forming.
So nucleophiles attack pi bonds and oxygens, and then bases attack
Nucleophiles do not attack pi bonds. Nucleophiles attack
oxygen,
electrophiles.
electrophiles.
Okay? So I know what you're trying to do is come up with a thing where they always attack this atom or this position. It doesn't happen. Okay? They will never attack pi bonds. Why won't they attack pi bonds? What is a pi bond?
A nucleophile?
A source of electrons. A nucleophile is not going to attack another nucleophile. What it will attack is the polar aspect of it if that pi bond is polar. This is why we haven't seen nucleophilic additions to alkenes, because alkenes are not polar, which means there's no difference in charge. Okay? So both carbons are effectively negative. With a polar pi bond, now we have a difference in charge. That's why we can get an electrophilic attack, or a direct electrophilic attack.
I just had something like that in my notes.
I don't know what to tell you.
So you gotta erase that.
This one becomes interesting because what happens once we remove that? We'd now have a negative charge, right?
Yeah.
Okay. We do have all the resonance and stuff, and we could address all that, but ultimately we're going to go back to the keto form. What do we do with that negative?
We attack bromine.
We attack bromine. We'd form that structure, right? This is where we'd say we're all happy and done, right?
No.
What is the problem with that structure? Or are you saying no just because?
Well, you've got a second step that you haven't taken into account at all. So,
Okay, what can you tell me about that structure? And in particular, what can you tell me in comparison to this structure? Don't worry, while you're thinking about it, I'm looking for a reference for you.
it was, the carbon is fighting over electron form. Or those carbons are going to be electron poor. That's a way to say that. It sounds sciencey. Those carbons are going to be electron poor because they've got two very electronegative elements.
You can do better than that. You're like, what? Yep, you can do better than that. Better not have deleted that question. Did I remove that question from the exam? You've got to be shitting me. Oh no, question 4. Question 4 from the exam. Wasn't looking at the right page. I'm asking you to compare 2 structures, right? Those 2 structures look an awful lot like structures
On the screen.
1 and 2 from the exam, huh?
Yeah.
What are you being asked to rank in question 4?
Acidity,
And according to acidity, which one's more acidic?
number 2.
Which is which one up here?
Neptune.
Okay, the one with the bromine, right? If this is more acidic than our starting material, and we're in a basic solution, what's going to happen?
More neutralization.
This is going to react again. Okay? It's going to remove another hydrogen, making another nucleophile, putting on another bromine.
And again.
And then there's still an even more acidic hydrogen in that structure, which means it does it again. Right? Once we've replaced all of those hydrogens, then it stops. Then we get some really goofy chemistry, which we'll talk about in a little bit. Okay? Why did that reaction all of a sudden change from the above ones? Because the previous ones, it just did it once, right?
Well, when you put it in basic conditions, you change the
It's the conditions that we run under. Basic conditions, the product that you make ends up being more acidic, so it continues to react. If we're under acidic conditions, the product is actually less acidic, so it doesn't react. In the top 1 neutral conditions, the same deal. As soon as we drop it into a basic environment, the product that we make from the first step ends up being more reactive than our starting material, and the reaction chains. Exciting. Okay? So that's one of the things that I typically like to talk about behind this, because a lot of people go through and say, well, how did they decide by looking at those reagents that they ended with this structure? By the way, don't stress. We'll talk about it in a second. How did someone just sit down and was like, oh, that's what's happened? They didn't. What happened? They sat down and they thought this was going to happen. And then what happened?
The other else.
It didn't. It didn't happen. Something else happened, and they had to backtrack through to figure out what that process was, what that thing ended up becoming. They had to work through all of those mechanistic steps to explain how we could possibly go from what you predicted to what you ended with. For those of you in lab being like, God, this sucks, this is awful, welcome to the epoxide lab. We literally set out to do a particular reaction, and it is ultimately going to fail. You have to be able to look at the end result and say, how the F did that happen? Okay? And to piece together how that could come about. Okay? That's how mechanisms come about. It's not someone just sitting down and being like, ta-da! No, that's crap.
Well, I meant who just found out about an atom.
So what we might then go through and do is, well, why do we do this? Why did they figure out an atom? Okay, what was the point of trying to figure out atoms?
Figure out how things work.
But how did you get there?
How did we get there? Why did we bother to deal with science? What were we trying to do?
Solve problems.
Just to see like
To turn lead into gold.
Alchemy.
That's how this all started. This was trying to take something that was worthless and make it valuable so that I could now become a billionaire.
what would they even like see that in? Like they didn't have like IR.
You're right. So they would have to come up with scientific processes and notes and processes to slowly work our way through to see what happens, to be able to control. Because when I mix this and I see a weird result, I have to be able to trust that that weird result is due to the chemistry of things that are mixed in there and that I've put those things in there. Because what if I thought I only put in Br2?
So are they capable of it?
Okay. Were they capable of it when this was discovered? Yes.
No, I mean making gold.
No.
No.
No. Okay. These are more synthesis type questions. Let's take a look between these two, because this is one that we should be able to reason through. So this is what I was kind of hoping for. What do we see as similar between these things? Where's our reactivity? Carbon and bromine, that's on a reactive site. So in our starting material, we only have one reactive site. Okay? We go to the product, where do we have reactive sites? 1, 2, 3, 4. We have 4 reactive sites. Okay? Everywhere there's a polar connection. Okay, what other big changes have we seen between these?
You added oxygen and got rid of bromine.
Okay? And oxygen has appeared. The bromine has disappeared. Okay? Sometimes you have restrictions. The restriction on this one, you can only use this structure as your carbon source. Why is that problematic? How many carbons did we start with? 3. How many did we end with? 6, which means?
You have to get enough of that to make half its own product.
Okay. We're going to have to figure out how all of these carbons can be accounted for over here. Where's the most likely place that I could try and start breaking stuff apart? Okay, around the oxygen. We could go blue or we could go orange. What do you want to do? Okay. Ultimately, we won't find out if we're right or wrong until what? We commit and try it and see if it fails. If it fails, yeah, we found a problem. Okay. If it doesn't fail, yippee, we could keep running with it. Okay. So we could try the orange path. If we split that, what would happen? Right? Where did the electrons in that bond go? More than likely. To the oxygen. Why to the oxygen? It's more electronegative. What happened to the carbon?
It's positive.
It was positive. This is a nice break for us because we can now see reactivity at that carbon, right? And we also see how many carbons? 3. How many carbons did I start with? 3. We at least get the 3 for 3 match. Do we have the chemistry where I want it to be? No. Okay. So now I can kind of shift focus. How can I get from this structure back to that?
Can you?
Yes, I can.
Wouldn't it be easier the other way then?
Until you test it, you don't know. Okay. What's that? Hydride shift. Are we going to expect a hydride shift to put a positive charge out at the least substituted position? No. So it's not a bad idea, but that's not going to work. Okay. How could I stabilize that positive in a reasonable structure?
Put something else there.
But I want to keep the positive. So what could I put there? I could try and put a pi bond there. Would that be a positive position? So I don't know about that. What could I put there that would keep that carbon positive? Something that would withdraw electrons, right?
Yeah.
Oxygen could work. What did we say was the problem with our oxygen? Oxygen needs how many bonds? 2. If we put out a hydrogen, what's the problem there? That functional group now gives us multiple sites of reactivity. I only want the carbon to react. So while the oxygen is a good idea, we could come up with something better. What could we put there? Bromine. Decent leaving group. Cool. I've got a bromine, a halide. But I want the halogen at the other position. Okay, which means the chemistry had to move. How do I get chemistry to move from one position to another? Does a substitution reaction move reactivity?
No.
No, so substitution's wrong. Would this be acid-base? I see you, give me a sec.
No.
No, so acid-base is wrong. Radicals?
No.
Radical would shuffle hydrogen for bromine, not bromine for bromine to different sites. So radicals out. Addition?
No.
Addition outright doesn't move the chemistry. Addition starts with two reactive sites, both positions of the pi bond. Okay, so that's a possibility. But then I would need a pi bond.
Which means you need an elimination.
Could I possibly pull this off? Okay. We're doing an addition here, right? What did we add? Hydrogen and bromine. So we could do HBr. So that's a possibility, right? Okay. I heard anti-Zaitsev. Becomes a bit problematic because Zaitsev is elimination, and this is doing addition. So how do I get the anti-addition? Don't know? Write HBr and say, what the F? We need something else to cause that to happen. You've acknowledged that you know something has to happen there. Can I go from the secondary bromide to this guy? To the pi bond. What kind of reaction is that? An elimination. What would I need to cause an elimination? Okay. So remember when I said we've got these reactions and you need to know the basics of these reactions. If you don't know the basics of these reactions, you need to figure them out. Why? That's the silence that you're hearing. You don't know the basics of those reactions, so you don't know how to reverse these processes because you don't understand what's happening at the very basic level first. That is the goal of OChem 1. Okay? For those of you who didn't have me for OChem 1, don't be thinking like, oh my God, I'm so far behind. Everybody is silent, even the half of the class that had me for OChem 1. Okay? We have to practice those pieces so that you can figure those steps out. If you don't practice those pieces, you will not be able to complete these. Yes?
Are we trying to figure out the WTF for the addition?
There was silence, so we moved on.
Well, for that, you need a base.
No. To go from here, and so you're thinking reverse. From here to here,
Yes.
what would you need? A base. Because in an elimination reaction, it is the loss of the leaving group and
A
hydrogen. So you need a base. Do we care what base we use in this case? Not really. Okay, it is a secondary structure, which means if we used a small base, what could potentially happen?
Inversion? Rearrangement?
No,
Nucleophilic attack. Because bases can also act as nucleophiles. Hence the reason we need to be able to differentiate between a base and a nucleophile. So if we picked a small base, we could likely get a substitution reaction happening here. I don't want that.
So you need a bulky base?
So we would need a bulky base.
T-butoxide?
T-butoxide. Phenomenal. We've got the ability to move through to generate our cation as an intermediate.
But one question. Wouldn't a positive move to the middle carbon?
The positive, if we formed a carbocation, would absolutely rearrange. So when we react these two, do I want to react it where I'm forming a carbocation?
No.
No, I want to react it where I don't form a carbocation. I want to react it in such a way that what kind of reaction am I doing?
SN2.
An SN2. No carbocation, no rearrangements. Splitting it that way gives us an idea of where the chemistry falls. Now we can start to predict things out of that structure. And we could decide, oh crap, that's going to do a rearrangement, which might very well mean we shouldn't have done orange, we should have done blue. Does that make sense?
Yeah.
The only way you know that is if you can see all of these pieces. How many of you saw any of those pieces before we drew them? Okay. How many of you wrote down any of those pieces? Okay. So you aren't seeing the pieces and you aren't writing them down. And you're not reviewing the basic fundamentals of what those reactions are. Okay? I understand we all have time commitments, but there's minimums to achieve a grade in the class. Okay? It is that practice that you have to be working through and you have to be poking at to come up with ideas to move through. If you're not doing that, you won't progress forwards. Okay? Even if you are doing that, you may not progress forwards. Okay? That is the tricky part of OChem. Okay? But that practice is a requirement, otherwise you are just guessing. Okay? And believe me, at no point will I accept 25% as a passing grade in the class. Yes?
So, are there multiple ways to get this?
Are there multiple ways to solve a synthesis problem? Absolutely.
Couldn't you do a Williamson ether synthesis?
What are we actually discussing about doing here? I've got a negative oxygen reacting with an alkyl halide. That looks an awful lot like a Williamson ether. But I needed those pieces to complete it. The Williamson ether was really just the last step. I was told I had to start with that. That's a restriction on the synthesis. I have to figure out how to get my pieces to that. That's why it becomes challenging. Is you might be, I've memorized Williamson ether. But if you can't place Williamson ether in the context of an addition reaction and an elimination reaction, you can't go anywhere. That's what makes synthesis so challenging. And arguably the best review for OChem that you can possibly have. Because it forces you to go back and look at all of those reagents and see those pieces. Okay? To figure out those reagents, you have to know where to search. You would have to know what changes you're making to the structure. What kind of reaction are you attempting to do? Substitution, elimination, addition. Because our textbook is organized that way, you can find those pieces. If you're using a different textbook, you can still use that other textbook. We'd need to be looking at reactions of alkyl halides, reactions of alkenes. Right? So it doesn't matter the textbook. All of those pieces are still there. They're just going to be organized in different fashions. Okay? Fun part of this, we just solved out what? Half of the question. Where the hell did those carbons come from? Okay?
From an alcohol?
We could say from an alcohol. Okay, but remember our restriction. We could only start with those 3 carbons. This structure here is not that structure. How do I go from there to there?
Wait, so both of them have to be done?
Your only carbon source is this molecule. That's a carbon source. You have to be able to connect those dots to. Yes?
That was like one of our intermediates. Do we react it with, can you use the information you got from one side in order to fill up the other side?
Yes!
So,
Right? And a lot of that depends on the symmetry of your structure. I intentionally picked a molecule that was relatively symmetric that would allow for some overlapping of pieces. Because we could have started with this to get here. Doesn't that look an awful lot like that guy?
It's just missing an alcohol.
It's just missing an alcohol. Can I go from this alkene to an alcohol in one step like that?
No.
Okay? That would be a substitution reaction, a hydrogen for an OH. Do I know a reagent that would do that?
Yes.
Yeah? What reagent? What reagent substitutes hydrogen for OH?
OSO4.
No. What I believe you're referencing there would be sulfate or sulfuric acid. I add sulfuric acid to this, I'm not going to go there. If anything, I'll start heading the opposite direction.
Peroxide.
Okay. Peroxide will do an epoxide, which could theoretically work, but I lose the pi bond in the same process. Okay. Starting to see how the connections can be challenging. Throwing out reagents isn't a bad idea, as long as what else are you doing?
Making sense of them?
Drawing them. You have to take that extra step of drawing that piece. Why? Because at best, there's two people in this classroom that can visualize these structures without having to write them down. At best. And arguably, the two people that think they can aren't doing a very good job of it. And if they wrote it down, they would be a lot more successful. Okay? The biggest thing that you should be doing to help yourself through OChem is to write it down. Yes?
So is that the best way for the synthesis problems? You break it and then you figure out how to get from
Yep.
to the original?
Yep. That's exactly what you're trying to do. Okay? This process that we've been using with these, I'm not sure what to call those. They aren't double arrows, but thicker arrows, if you will, is known as retrosynthesis because we're thinking backwards. Okay? You could try and look at this piece and say, what could I do to go here? Okay? Well, how much do you have to do to go from there to there? Okay? The laugh suggests a problem. You have to do a lot. Okay? So that can be a challenging process to weed through. If you at least make one break, now from here to there, that's a lot smaller of a step. Does that make sense?
Reagents are going to be the ones the same answer?
You're not mirroring the reagents on pieces. You're just trying to identify where those pieces are to help you move through the synthesis. That is it. Okay? How do you process through that? Okay? And I'm starting to hear questions of like, whoa, we can just copy from both sides and just shuffle. No. What you're now trying to do is take rules from this question and apply them to all questions. No. What was the process we went through? Identify where it was reacted. Okay? In both the reactant and the product. Identify constraints. We can only use this as a carbon source. Okay? Identify your functional group changes. Where are there major breaks in reactivity? Looking for your carbon skeleton. Those are the patterns. Not how can I break this so that I can do two different systems at the same time. That's this question. Don't start making rules for one question, apply to everything else. Okay? That's a big mistake. Okay? Some Diels-Alder practice. We're just going to talk real quickly about this. We've got sigma up and sigma down as patterns. Right? Those are your patterns to help you kind of focus through. The problem with Diels-Alder is you get both sigma up and sigma down. Both reactions are a result. If you draw one of them, you may not be drawing the one answer shown in the multiple choice. So you are responsible for those three-dimensional manipulations to get it to look like that one answer. Okay? In my OChem class, that's Unit 1, Structural Manipulations. Okay? When we run a Diels-Alder reaction, we form a cyclohexene. Cyclohexenes can adopt chair conformations, which means not only are you responsible for drawing just out the cyclohexene and recognizing all the pieces, you have to be able to visualize that in 3 dimensions when it occupies a chair shape. Okay? All of these things are pieces that stack in OChem. Regardless of where you take it, you end up being responsible for it. It's just a question of how it's called out. In some cases, it's not called out, and you're just expected to figure it out. How? Memorization. Okay? Nitrogen. When we look at an amine, what chemistry do we see available to it? So now we're going to take a big, massive step down, breathe a little bit before we turn it into a mess again. What's the chemistry we see for the nitrogen?
Acid base.
Acid base. Where's acid base? Because acid base is two chemistries.
So it has acid and base. It has hydrogens and it has a lone pair, so it can act as an acid or as a base.
We have hydrogens and we have lone pairs. Is the amine acidic?
Not terribly.
The pKa of that hydrogen is about 32. I think it's actually 35, but I'm just going to say 32. Is that acidic?
No.
Water is 16. That is 10 to the 16 times less acidic than water, which means nitrogen is not acidic. I want to be careful with that statement. Just because it is not acidic doesn't make it basic.
If it's less acidic than water?
This compound, CH4, has a pKa of about 50. It is not acidic. Does that make it basic?
No.
To be basic, what do we need?
A low pKb.
So we could reference a pKb, are irrelevant.
You need to be able to give up. I mean, you need to be able to accept hydrogens.
You need to be able to accept hydrogens. To accept hydrogens, what does the structure need to have?
Lone pairs.
Electrons. Does CH4 have electrons? No, not basic. Okay? What is happening is you are falling into the memorization trap of, if we look at the conjugate base, the conjugate base is now exceptionally basic. Different structure. Okay? Super common misconception that I think falls from 152. Okay? So, with the amine, is it basic?
Yes.
Does it have lone pair electrons? Yes. Okay? So yes, the amine can act as a base. Okay? So it can donate those electrons out. If it acts as a base, what else might it act as? A nucleophile. How about that carbon? Should that carbon act as an electrophile?
It could.
Yeah.
It could, with the same likelihood that
The amine will act like
that the hydrogen would act like an acid. Did the hydrogen on the amine act as an acid? No, which means carbon doesn't act. We really only get the nitrogen lone pairs doing anything useful for us. Okay? So now the question is, what could we do with that?
So it's not like OH where it can do all sorts of things.
Nope, it's not like OH. Why is it different than OH?
Less electronic.
The electronegativity has changed. It's that difference in electronegativity that's causing a major shift in how it reacts. Okay? So it could act as a base or a nucleophile. The nucleophile chemistry is new to you. The acid-base chemistry should not be new because you've spent 2 years already doing acid-base reactions. That's what Gen Chem is all about. So if we go through and look at its nucleophile chemistry, the nitrogen can attack an electrophilic carbon, where we have a leaving group, and we produce our product. So we'll do some subtle erasing. Does that look familiar to anyone? I heard some flipping. So flipping through some notes is not a bad idea. I would actually argue that page 2 of your exam is a good place to look. Let's say question B, part B, compare the reactivity of an amine to a primary amine. We just said these structures were both bases. Are they both equally basic? No. How would their chemistry change? What is the difference between these? Carbon versus hydrogen. Carbon has more electrons than hydrogen. Guess what the carbon can do? Donate electrons in. Which means nitrogen now has more electrons, which means it is more basic or more nucleophilic. What was the reaction we just ran? A nucleophilic substitution. The product of that nucleophilic substitution was a stronger nucleophile than we started with, which means it's going to react again. And it's going to react so much and so randomly that what we end up with at the end is a mixture of amines, primary, secondary, tertiary, and quaternary. All of them. Is that a good reaction to run?
No.
No. So as far as substitution goes, guess what we say about amines?
They're not good.
They're not good. We entirely ignore their substitution reactions with one sort of extent. I can alter the reaction to get one of these products. What do? So 4 answers. Worst case, 20% chance of getting it right? It's not bad.
You can force it a particular way.
I can force it to make one of these answers. Which of those answers can I force?
Number 1.
Go with C.
The only one we can force is D. The one forming a trace amount. How do I force that?
Negative solution.
Whoops. Throw in an excess of the alkyl halide. There's now so much alkyl halide that what happens? It'll keep reacting, and I can force all of them across to the quaternary amine. And you might ask, why the hell would I want to do that? I do it for that. Taking it to an elimination reaction. We'll pick up there Wednesday.